If you've tried to buy a high-end GPU lately, you've noticed that the prices have skyrocketed over the past couple of years. The AI industry has created a massive demand for common GPUs. For big, high-performance models, this is best exemplified by the massive cost explosion in training recent LLMs. Companies require huge stocks of these GPUs because their performance is relatively limited. We are forcing these digital chips to do something they weren't designed for. The fundamental problem is a mismatch between architecture and application. Standard CPUs and GPUs are built on deterministic logic. They are designed to be precise. Input A plus input B must always equal result C. To achieve this precision, we engineer these chips to completely suppress external interference, specifically heat and thermal noise. But generative AI is probabilistic. It doesn't want a single precise answer. It needs to sample from a distribution of possible answers. It needs randomness to function. Because our hardware is rigid, we have to simulate this randomness. We force the GPU to run complex, pseudo-random number generator algorithms. We are effectively burning massive amounts of computational power just to fake stochastic behavior on a machine designed to reject it. This is the core inefficiency. We spend energy cooling chips to eliminate thermal noise for the sake of precision, and then we spend more energy running heavy algorithms to reintroduce randomness. The result is that AI currently demands huge amounts of chips and huge amounts of energy just to run. This is the reason that led to the idea of the thermodynamic chip, which some people believe might change the game. At the heart of these thermodynamic chips is a new fundamental component called the probabilistic bit, or p-bit. We start with the fundamental physics of the p-bit. Unlike a standard digital bit, which uses a high-energy barrier to lock data in place, we design this system with a low-energy barrier between the 0 state and the 1 state. This specific energy landscape allows the ambient thermal noise, the heat already present in the device, to drive the system, causing the state to fluctuate continuously between the two values. We implement this concept using a device called a magnetic tunnel junction. This component consists of a fixed magnetic layer, which provides a stable reference, and a free magnetic layer on top. The free layer is engineered to be thermally unstable. This means its magnetic orientation rapidly flips back and forth, driven purely by the thermal energy in the silicon. The result of this magnetic fluctuation is a stochastic voltage output. As you can see in the graph, the signal does not stay at a static 0 or 1. Instead, it transitions rapidly between high and low voltages over time. This generates a native stream of true randomness directly from the hardware's physical behavior. Finally, we connect this output to the AI neural network. Because the signal is naturally probabilistic, we can use it to perform sampling tasks directly. The neural network utilizes these hardware fluctuations to process distributions and weights efficiently, without requiring complex algorithms to simulate randomness. While this theory has existed in academia for years, Xtropic is the first to build a commercially viable thermodynamic sampling unit, or TSU. Their prototype, the XTR0, acts as an accelerator. Just as a GPU offloads graphics rendering from the CPU, the TSU offloads the heavy lifting of probability sampling from the GPU. They have also released a software stack called Thermal, which allows developers to write algorithms that compile down to these analog physics processes, effectively bridging the gap between Python code and thermal noise. Xtropic claims that by shifting to this thermodynamic architecture, they can achieve orders of magnitude improvements in runtime speed and energy efficiency for generative AI. They aren't targeting a 10% gain. They are targeting an exponential shift. To be fair, this sounds incredibly far-fetched. We are talking about abandoning the absolute reliability of digital logic for a system based on noise and fluctuation. It is a radical departure from 60 years of computing history, and the engineering challenges of making analog chips reliable at scale are massive. Right now, it is a fascinating, scientifically sound concept that might work. It addresses the fundamental physics bottleneck that the current industry is hitting. But until we see these chips running heavy workloads in a real server farm, it remains just that, a very cool, very high-stakes experiment in material science.